So this week, we are going to talk about the remaining topics of elements of probability. Once again, I have to acknowledge the resources that I used to create this lecture. And this is the basic outline of the topics that, excuse me, the topics that we have in this chapter. And if you recall, we already covered sample space and events. We've talked about the algebra of events and axioms of probability. As a brief review, I'm going to go through it once more. So first is about the sample space and events. Allow me to correct myself a bit, as last week, I believe I misrepresented the sample space. So what I did last week was something like this. So I denoted the entire universal set or universe as S, which was in fact incorrect. So please disregard that from last week. And the correct way to denote it is as follows, because the sample space, AKA everything that could happen, may not constitute the entire universal set. So that's the only change, that the sample space is within the universal set, but everything else within it is still the same as we covered last week. And once we know all of the sets or events that are involved in whatever it is that we are considering, we can also combine these events in such a way using set theory, which all of you should already be familiar with from your previous courses. So we could denote the complement of E, like for example, complement of E, and if this is E, then obviously the complement is everything outside of E. And then we can also denote a union. So in this case, we have E and F. So we can denote the union, or this is also often written as EF, which is the joint areas in the Venn diagram of E and F. Next, we can also have the intersection of E and F, which is this sliver in the middle here. Both E and F are valid in this area. And also we can denote, subsets with that, and a proper subset as follows. So if I had a smaller subset like that, I could write G is a subset of E. I could also write G is a proper subset of E. But say, for example, if I had an identical set, another set here, which is, for example, H, E, F, G, H, then I could write H as a subset of E, but I cannot write H is a proper subset of E because H equals E. So do not use this for non-proper subsets of E. And lastly, after we were introduced to the concept of probability and how we can define all of the events that could happen or could not happen, we have some axioms. So first, we have the rule that all probabilities must be denoted between the values of 0 and 1. So it's not possible for us to say the probability is 2, for example, and the probability of the entire sample space will be 1. And we can sum up the probabilities if and only if the events are mutually exclusive. So consequently, if we're talking about an empty set, the probability will be 0. If we're talking about a complement, it will be 1 minus the event, because everything else combined with the event E will constitute the sample space, and thus it should be equal to 1. And if we have simply P probability of E union F, we have to consider in case E and F are not mutually exclusive, and we have to subtract the probability of their intersection. So we can only sum them up simply if we know that they are mutually exclusive. And finally, when we're talking about subsets, if A is a subset of B, then its probability should also be less than the probability of B. And next, we talked about the idea of sample spaces having equally likely outcomes. So in this course, we are going to assume that this is the case, this is valid, that all possible outcomes are equally likely, although in some scenarios in the real world, this is not always the case. Sometimes there are outcomes that are more likely than the others. But for the sake of this probability class, we assume that all possible outcomes are equally likely, and thus we can compute the probability of any event as follows: the number of the number of outcomes in the event and the number of total outcomes in the sample space. And when we are trying to count these members, these outcomes in every single possibility of something happening in an event, instead of us writing down every single possibility, which you could do and is a valid way to solve the problem. However, it's not the most efficient way to do it. So in order for us to do it a little bit more intelligently and also efficiently, we can use some rules in order for us to determine the number of members, the number of outcomes in a certain combination of events. We talked about the product rule, permutation, and combination, as well as circular and ring permutation. So now we're going to talk about conditional probability, which is the basis of the Bayesian theorem that I introduced to you in the video in the beginning of the class. So from the name, you probably can get a good idea what it is. We're talking about conditions, conditionals, ifs. Like, for example, if I were to ask you, what's the probability of it raining today? You could probably give me a number based on your experience, for example. However, if I had told you some other piece of information, like, for example, yesterday it rained, or during the whole last week it rained, perhaps that additional condition, that additional information could change the probability that you gave me when I asked you, what's the probability of it raining today? This is how we are trying to define a certain probability based on another event that happened, another outcome, set of outcomes that we know have already been proven true. So we can define conditional probability as the probability of event E given that event F has occurred. So we're trying to compute E, but we already know that F has already happened. In order to write it down, we denote it as P E given F. So this piece here, you can it's usually read as the probability of E given F. So we know that F is already occurring. In this case, we only consider the event E if F is valid. So this F becomes our new sample space because all of the events that could happen must involve F, because we limit our E events only to that happens with F. So our new sample space becomes F. So if you remember, when we're trying to compute the probability of a certain event, we compute the number of members of the set of that particular event, as well as the number in the sample space, right? But since our sample space has now changed to the event F itself, so this bottom part changes. So it is the number of outcomes, or you can also write it as a probability itself, because then it's the same thing. The ratio is the same. So we have P probability of E happening given F equals the probability of E and F divided by F. So I'm going to draw it out here for you just to make it clear. This was our universal set, right? This is our initial sample space, our initial sample space. This is E, and this is F. At the moment, we want to consider the probability of E, which in normal circumstances, the probability of E would be this entire circle, right? But now we have an additional conditioning to this E that we're trying to compute. We only want to know E given F. So I want to know the probability of E happening if F happens. So what we are actually considering is this particular area. And since F is the conditioning case, so we need to know if F happens. So this is our entire sample space here. So logically, when you're trying to compute a probability, we know that we need to compute a fraction, right? We need to compute a percentage, a fraction. So what's the probability of this area? Sorry, I should change the color. This thing, this part happening, given we know F is happening. Obviously, this is quite simple since we already know the set theory. So if I wanted to denote this in a fraction, then it would be equal to EF divided by F, the number of EF divided by the number of F, or equivalently, the probability of EF divided by EF. This is for the probability of F has to be more than 0, obviously. If F does not exist, aka the probability of F is 0, then it is pointless to compute EF because, you know, remember in calculus, if PF equals 0, then I would have a divide by 0 problem here, which is not doable in mathematics. So we have to have this assumption that the probability of F must be larger than 0. F is also called the conditioning event. So if we talk about the probability between E and F as follows, then we have two specific conditions. If the intersection between E and F, so this middle area here, this intersection here, the red area in the middle here, is equal to an empty set, or we can also write it like that, then obviously the probability of EF is also 0, and thus PE given F will also be 0. And if F is actually a subset of E, so if I redrew this and E is like that and F is like that, for example, so imagine if I have the probability of E and F divided by the probability of F, and E and F is this area, PF is also the same area, then I would get equals 2, 1. So, oops, I think I have a typo on my slide. Apologies. Please give me a moment to correct it. Okay, I think that's okay. And then we have these two rules that follows as a consequence of the conditioning of E and F. So first, I would like us to correctly denote or define the events. So first, here it was already done for you. It says E is the event that the red die gives the number 5. F is the event that the sum of scores of the two dice is 6. So we are going to write that correctly, each of these events. So here is the event E, and here is the event F. So E is all cases in which the red die equals 5, which if we consider two dice, then we can write it as follows. And here, assuming that the red die is the first one, okay, that was just arbitrary. And the second one is the sum of scores of the two dice is 6. So these are all of the cases that could occur to fulfill F. So now we are going to define, we have the probability of E, which was this event here. We know that there are 6 events. Outcomes, my bad, outcomes. And when we're talking about two dice, we know that there are a total of 36 possibilities. So if I write that down simply, we can get 1/6. So when I consider F, I know that there are 1, 2, 3, 4, 5 outcomes here. They're 5 over 36. I can't simplify that further. And if I were to denote what is the intersection of F, we have this event here and this event here. I believe this is the only event that is present in both, the only outcome, apologies, the only outcome that comes up in both events. Thus, we can also write this as one event over 36 because there are 36 events in my sample space. So if I were to follow that golden rule of probability, what is the probability of E given that F has occurred? So this is the question, given F has occurred, what is the probability of E? I can follow that golden rule here. We're going to see this very, very often. So please don't forget this little friend over here. I'm going to write it up on the top right corner so you guys know how important this is. F divided by PF. And here we can compute PEF. We know it's 1 over 36. We know PF is 5 over 36. And we know that the total is 1 over 5, or in other words, 0.2. So in this case, we wrote out all of the possible schemes, right? We wrote 5.1, 5.2, and so forth. But we don't have to do that in all cases if it's a little bit, it's not convenient. Don't forget to also utilize what you know about combinations, permutations, and so forth. So here is a second example. Honestly, I took this from the previous slides, and I don't really like the wording of it. So let's go through it together. So an employee is invited to attend a party along with his youngest son. So we can, I'm going to assume here that if I don't have a youngest son, then I won't be invited to the party. So we know that Jones has 2 children. And what is the conditional probability that they are both boys? So given that he is invited to dinner. So if we know that he has 2 children, he's invited to the dinner. So we know that at least the second child should be a boy. So these are the cases. So the event that we define the events correctly. B is boy, G is girl, and the sample space is thus as follows, because we know that he only has 2 children. And we assume that the outcomes are equally likely in the case that the conditioning is fair. And thus B is the event that both children are boys, and A is the event that at least one of them is a boy. And thus, what is the conditional probability that they are both boys? So the probability of B, given that he is invited to the dinner. Since he's invited, we know that at least one of them is a boy. And thus, I think it's already pre-computed. We can compute the probability of this condition here. So as I mentioned, we don't have to always write down every single possibility. And we also have lots of ways to do so. If you recall, there's the multiplication rule and so forth, which is also valid for conditional events. So I'm going to talk about a hypothetical event A and a hypothetical event B. So if I have one event, I have an event of A given B. Remember this handy equation that I wrote in the top right corner in the previous slide. We know that the probability of A given B can be computed by dividing the probability of A and B divided by B, like that, right? We know that. We already went through that. That's the equation of conditional probability. If I wanted to rewrite this, I can move things around, and I could write the probability of AB as PB times PAB. This is nothing fancy. I'm just multiplying this and this to get PAB. So I'm just moving around the equations. Say I also have the condition of B given A, then I can compute this as P BA. However, B intersection A is the same thing as A intersection B, right? So I can also write it like that. And I divide it by PA, and thus I can have PAB defined as PA divided by PAB. See here that then I have PAB here. I have PAB here as well. And thus I know that these two equations are equal. So I can compute the probability of the intersection using either the conditioning based on B as well as the conditioning based on A. Okay, so now say I'm talking about a third hypothetical event. Let's say C, for example. I have C and I want to know what's the probability of C if I know that A and B happened. So I'm talking about this hypothetical intersection. So if I know that AB happened, how can I determine what the probability of C is? So once again, using our trusty conditional equation, I can write this as probability of C intersection AB, which I can write in any way I want. I could write it ABC, I could write it BAC, I could write it CAB, divided by PAB. Or if I write PABC, then I can write it as the multiplication of PAB times PCAB. Oh, wait, didn't we already define PAB up here? We did. So I can also write this as PA, PB given A times PC given AB. See a pattern here. So we're talking about the probability of a conditional event, and I'm now talking about the intersection of three different events. I can compute it based on, starting from A, I multiply it with B given A, C given AB. And you probably can guess where this is going. If I add on a fourth event D, a fifth event E, and so forth, then I have a chain rule. I can define the intersection of a series of N events as long as I would like. So based on this general multiplication rule, I then can solve this problem, in which I say that I have a box containing 10 red balls and 10 blue balls. So I have box, I have 10 red ones, I have 10 blue ones. If 3 balls are selected randomly without being returned each time, what's the probability that all 3 balls are red? This is quite important, this part, without being returned each time. So assume that each ball has, this is obviously a typo, has the same probability to be chosen, aka equally likely. So we can compute using the multiplication rule. What is the probability of first taking the first red ball, taking the second red ball, and third red ball? So first, the probability of 1 red ball, the probability of the second red ball, and the probability of the third red ball. The first time, we know that the probability is 10 over 20. We have 10 and 10. The second time, when I already have a red ball, so we assume that the event A1 is already happened. So we know that there are now one less red ball. And the probability becomes 9 over 19. And thus 8 over 18 using the multiplication rule. I think that is correct. Let's check. Yes. And here we have the probability of 3 sequential events. Okay. So we're talking about more than one event, right? So if I am talking about a certain event E, so here is my Venn diagram. If I have E here, I could define the probability of, I could define the event E as a union between EF here and EF complement, because I wanted to define E as a combination and how it is related to EF. So let's see, what is EF? The combination of, what is E and F here? The intersection, it's this area here, F, and E intersection F complement, it's this area here. So this is E. So based on that mindset, I know that EFC and EF are mutually exclusive. We know that there is no other intersection between these two parts. Just to make sure, I'm talking about this area and that area. So then I can attempt to define PE as a sum of PEF and PEF complement. I am allowed to do this because I know that EF and EFC are mutually exclusive. Then, don't forget that I'm not allowed to do this if I know that there is another intersection. I have to subtract and so forth. But we know that they are mutually independent. So I want to now define PEF. Remember, when we were talking about the conditionals, when we were writing down PA equals, E given F, let me go back. This is the one I'm referring to. So we know that I could redefine my probabilities back and forth based on A, based on B, and so forth. So now when I'm defining EF, E and F, I could define it as PE given F times PF, okay? And I also can define this as PE given F complement times PF complement, okay? So we know that these are complementary, F and F complement are complementary, and if I sum them up, it must equal 1. So in other words, I can write this as PEF plus PE given F complement times 1 minus PF as follows. So I can define E based on another event F. So here I'm defining E as to if F happens and if F does not happen. So in that case, we can compute the total probability of E, determine the total probability of a certain event, in our case E, by a certain condition of another second event, which in this case we use F. I'm going to try to illustrate that better in an example. So I have an insurance company. I know that there are two types of people, those that are accident prone and those that are non-accident prone. Their statistics show that an accident prone person will have an accident with probability 0.4. Okay, so we're going to try to define this statement together, okay? So their statistics shows that an accident prone person, let's write it, F is an event that the holder is accident prone. A is an event that an accident will happen. So an accident prone person will have an accident with probability of 0.4. That means I know that they are accident prone. And the probability that an accident happens is 0.4, aka the probability of an accident happening when I know that the person is accident prone is 0.4. Next, the probability decreases to 0.2 for non-accident prone persons. So I can also write the probability of an accident happening if I know that the person is not accident prone is thus 0.2. If I assume that 30% of the population is accident prone, then I can write it as PF is 0.3. And thus, if I wanted to compute the total probability that an accident will happen, I can write it as a condition based on the conditioning that people are accident prone. Thus, I can write the probability of A given F for accident prone people and the probability of A given F complement for non-accident prone people. And we can compute that real quick. I think here AF F plus that times 310. Okay, I think I already computed it. Let's hope I already computed it. Oh, it's back there. Apologies. Let's delete the writing then. Thus, it is a 0.26. So here you see that I'm trying to define the probability of an accident based on this predefined condition, if the person is accident prone or not. So up until now, we talked about two different conditions only, a binary case in which people are either accident prone or non-accident prone. In this case, we're talking about it's either F or, apologies, F or not F, F or F complement. Let's try to extend that into more than two cases, not just a binary case, yes or no. So now if we consider any case, so any event based on another event, and we have more than one probabilities for that event or each condition, if we generalize that, then we know that the sample space of the condition is the union of all of these conditions. Assume that each of these conditions are mutually exclusive. Like that, the previous one, the accident prone and non-accident prone, these things are two mutually exclusive things. But here I already showed you. So here, since we're trying to combine, so we're talking about A here, A, this event A. Not only are we talking about it happening for a second event, but we're talking about it happening for various events. And thus, following the same pattern that we had in this one, the sum, here we only have the sum of yes and the sum of no. Here we're summing up every single case that could happen. So if previously we already had two conditions, yes or no, here we have so many different conditions that add up that we can compute to A. So this is the law of total probability, in which we can define the probability of A given one condition, given two conditions, and so forth, and conditions in total. So up until now, we have a bunch of equations that I hope you still remember. You don't need to memorize it. Never, I will never ask you to memorize it. However, I do hope that you get the point on these two things. First is the conditional probability itself, how we defined it, because F is now the sample space. This is one that I hope you remember. The second one is that previous sum law of total probability. So if we have a PA, I hope that you remember that we can compute it as a sum of PCN. So for all n's. Oops, never mind. Don't forget, this is the union, right? So this is the sorry, not union, the intersection, and which we can define as such. Okay, so based on these two things that we already know up until now, we now can define the Bayes theorem. It's based on, if I know how some conditions here, these conditions here, I know that these things could happen. I know these probabilities. I know the probability that it rained yesterday. I know the probability that it rained 2 days ago. I know the probability it didn't rain. I know all of these probabilities, C3 and so forth. And I also know the probability of it raining today, given it rained yesterday, the probability of it raining today, given it rained 4 days ago, and so forth, until we get to the probability of A given Cn. So I know the condition probabilities. I know the what will happen if these conditions occur. So here we have the prior probabilities, and we also have the likelihood of A. So what if I wanted to compute the opposite? So, okay, I know that these conditions could happen. I have the probabilities. I also know that A could happen given these conditions. But what if I want to know now the probability of it raining a couple of days ago, given that today it is raining? Flipping it now. And this is called the posterior probabilities. And this is what Bayesian probabilities. And this is what the Bayes theorem tries to compute. I want to compute what I don't know. I already know the conditions. I know the likelihood of A. What if I want to compute the conditions based on A? So the other way around. So if we go through what we already know, we can now define PC1. For example, I'm just choosing one at random. Any condition here, given A, then I can compute it as, I'll write it here, based on this equation here, this number one over here, P C1A divided by PA. Okay, this is based on this conditional probability rule on top. Next, PCA, this one over here, I can compute as PC given A times PA, I can, but I don't know this. But remember that I could do it both ways, right? Let's go back. This one here. Oh, if I don't know, oops, sorry, I just realized this is opposite. This is wrong. My bad. This is BA. This is the other way around. So I know that when I'm computing the intersection, if I don't have AB, I could compute it based on B given A. So based on that rule, then instead of me using C1 given A, which I don't know yet, I'll just do the opposite. I know the other way. I know the prior probabilities. So instead of computing C1 given A, why don't I compute A given C1 times C1? And here, when I'm trying to compute the probability of A, I look to the second equation here that I have, which is PA can be computed as a sum of the probability of the intersection of A with every other condition that we have defined. So here I could write down A given C1 plus everything we have up until PA times CN, apologies, times CN. These are talking about all of these probabilities, prior probabilities and likelihoods. And this is the basis of Bayesian theorem. This here is the Bayesian theorem. Okay, any questions? This together. So on a multiple choice test, so you have a multiple choice test, the probability that the student knows the answer is 0.4. So we already defined here, there are two events. So the event in which the student answers correctly and the event that the student knows the answer. So you use a lot of logic and common sense in deciphering questions like this. So let's write. The possibility that the student knows the answer is 0.4. So the probability that the student knows the answer is 0.4. That one is straightforward. Assume that a student who guesses the answer will be correct with a probability of 0.2. So here we use some logic. So if you're guessing, that means that you probably don't really know the answer. So in this case, we compute the probability of a student answering correctly when they do not know the answer is 0.2. And we're trying to compute what is the conditional probability that the student knew the answer, given that he answered it correctly. So what is the probability that the student knew the answer? Oh, sorry, that's wrong. That the student knew the answer. K, that the student knows the answer, given that he answered it correctly. So if we look back to our Bayesian theorem, I'm trying to compute K given C. Here, I know C given K complement. So if I want to compute K given C, I need to know all of the conditions of the other way around, of the posterior probabilities. So here I must be able to, I must know the probability of C given K, alias the probability of a student answering correctly given he knows the answer. Okay, so if I know the answer, I'm going to write the correct answer. I'm going to choose the correct multiple choice question. So here I'm going to assume that the probability of a student answering correct if he knows is 1. So this is what I mean by some logic or some common sense. Because here, this was not given to us. The P, C given K was not given to us. However, based on logic, I am making an assumption that the probability of a student writing it, answering correctly, given that he knows, is 1. If I know it, why wouldn't I put the correct answer? So what I want to stress here is that when you're defining your variables, when you're trying to solve the question, don't forget to write down these assumptions. So you're assuming that P, C given K is 1. Because when I'm correcting your answers, I'm not only seeing if you get the correct answer at the end, but I'm also trying to see how you're translating the answer. Because if you have this assumption, perhaps you will get a different question, a different answer to someone that did not assume the same thing. So please do not forget to write down all of your assumptions, all of the things that you derive from your assumptions, so that I can give you credit for your thought process. So here I'm computing the posterior probability of K given C. So I'm going to write how we're going to compute it. P, K given C. Sorry, not given, K and C. And PC, which we already derived previously as PC given K, PK, and PC given K, PK, plus PC given K, C, PK, C. That's right, yeah. And in this case, we now can compute the probabilities like that, yeah. And the final answer that we obtain is 0.71. Is that right? 0.1? Yeah, 0.71. So note here that our events in this particular example was based on some sort of assumption because it's not given explicitly in the question. Please know that you're allowed to do so as long as you denote it correctly in your answer. Okay, so we have a bunch of examples. I have a lot of examples of conditional probability. I believe that you can Google it. Even I sometimes look for inspiration when I'm, so we can only say of events E and F that they are independent if and only if I know the probability of their intersection, and I know that I can compute this equation is valid. What it means for two events to be independent is that whether or not event E happened, it doesn't change event F. So up until now, we talked about conditionals, right? So like, what is the probability of E happening if F happened, or the probability of E happening if F didn't happen? However, if we're talking about two different independent events, it doesn't matter. Whatever happens with F, it will not change the probability of E. Whatever happens with E, it will not change the probability of F, and vice versa. So as an illustration, this is one example of independent events. So I'm tossing a coin, and then afterwards, I immediately roll a die. So if I define my events, E is an even outcome, H is a head outcome, T is a tail outcome, I would like to compute all of these probabilities, PE, PT, and PE given T. So let's compute that. So I know that PE, the even outcome on rolling a die. So that means it's either 2 or 4 or 6. So I know that it should be, E should be 3 over 6 possible things. Next, when I'm talking about a tail outcome, I know that it's either heads or tails. So the probability of T is probably half. This is also equal to half, right? Okay, and when I'm talking about PE given T, let's try to compute that. PE given T is PET, PET divided by PT. Oh, I don't know this yet. Let's try to compute it. PET is EET by the intersection can also be written as PET, sorry, equals PE given T, PT. And PE given T, it genuinely doesn't matter, right? Whatever happens with T, it does not affect E. So we know that this is 0.5 and this is also 0.5. And this is equals to 0.25. So if we look at the equation here, let's try to check, is this equation valid? In this particular case, oh, I shouldn't have written, sorry, because it's messed up. So in this particular case, we know that it holds. If I were to consider these two events, tossing a coin and then rolling a die, then the probability of E and the probability of T multiplied is 0.25. The probability of their intersection is also 0.25, and thus the rule holds. In this particular example, I don't think anyone is surprised because I'm talking about two different physical objects. I'm talking about a die and I'm talking about a coin. Obviously, whatever happens here will not affect what happens. Whatever happens with the die will not affect what happens on the head, on the coin, and vice versa. They are two different things. They can't affect each other in that way. These two events are physically independent. However, using that argument, we're going to talk about rolling a die, one single die. So what is the probability that E, the outcome of the die, is even? So here the die is even, which is 3 over 6 as well, I believe, right? And then the outcome is larger and equal to 4. So it's 4, 5, 6. This is also 6. EF, an even outcome is larger than 4, that larger and equal to 4. So among 4, 5, 6, there are 2 of them that are larger than and equal to 4. And if we talk about the independence, so let's compute this. Oops, 6. Oh, I apologize. This is not larger and equal to 4, but smaller and equal to 4. So if I'm talking about smaller and equal to 4, that means 1, 2, 3, 4, 4, 6. An even outcome less and equal to 4, that means I'm talking about 2, 3, 2, 6. And I want to know if these two events are independent. So here we see that if we compute each of these events, PE 3 over 6, PF 4 over 6, and even outcome is 2 over 6. And if I were to compute the rule of independent events, the PEF would equal to the product of their respective probabilities. And thus, based on definition, I can say that E and F here are also independent events. So be careful with the term independent. It is not translatable in Indonesian to saling lepas, not directly, because on this particular example that we use here, this die is the same physical die. So it does not always mean that a physically dependent event will automatically be dependent. The independent events do not have to be independent physical processes. So as a discussion, if that is not what determines what independent events are, so it has nothing to do whether or not they're two different physical things. Because just now we saw two examples. One independent, they were independent physically, so obviously they are independent events. But the second one was physically the same object, so they're not two different physical things. However, based on the equation, on the theory, they are independent events. So what it means is that the info, the prior info that you have, that the outcome is less than 4, it does not help you at all in determining if the event is odd or even. That is why we say that they are independent. So basically, if you want to prove it mathematically, you need to just compute the individual probabilities, and you have to see if it fulfills the PET equals PE and PT. If it does fulfill, however improbable it might be in your head, then they are independent events, regardless of if they are physically dependent or not. So following that definition, there are some propositions. Don't worry about it too much. These are just things that happen in consequence of the concept of independent events. Then we can decide on what happens with their complements and so forth. And finally, sorry, and finally, as with all of the events that we talked about previously, we were talking about conditional events, we were talking about the multiplication rule. Obviously, when I'm talking about two different events and I add on a third one or a fourth one and so forth, I can generalize the independent events as follows. So here we have 3 events, which I can say that they are independent if the sum of all of their probabilities, the product of all of their probabilities will be equal to the probability of their intersection, so forth. So if we have 3 of them, then I can say that E will be independent as well of any event form from F and G. Any combination of F and G will also be independent towards E, and vice versa. So if we know that all 3 of them are independent, then any combination between E and F will also be independent from G and so forth. Okay, that brings me to the end of the chapter of probability. So I believe that we have one discussion up for grabs, the one that Alexander gave us today.